In this lecture, we'll see something known as a vector space. So what is a vector space? Vector space V for a field F. Okay, so a vector space is always defined in conjunction with the field. Okay. So there are some scalars that would be needed for defining the vector space, and these so-called scalars will be taken from the field. Okay. So vector space V over a field F is essentially a set of elements which will term as vectors. Okay, and this set of elements will satisfy certain axioms. Now the axioms that we are going to see are defined with respect to two operations. One which will term as vector addition, and another which will term as the scalar multiplication. Okay, we'll see the axioms with respect to these two operations. Okay, so we'll start with the vector axiom. The first set of axioms corresponding to vector addition. You take any pair of vectors from the set V. There will always exist another vector x plus y that is also in V. This is known as the closure. Take any pair of vectors from the set V. The vector x plus y will be same as the vector y plus x. This will satisfy the commutative property. Commutative property for the vector addition. Okay. You take any triplet from the set V. Triplet means any three vectors from the set V. They satisfy the vector addition satisfies the associative property. Next, there exists a unique element, or we can say there exists a unique vector denoted by 0 in V such that for all the elements, for any element that you or any vector that you take in the set V, x plus 0 will be same as 0 plus x, and this will be essentially equal to x. This is additive existence of a unique additive identity. Corresponding, you take a vector in the set V corresponding to that vector. Okay, I should write it like this. To every vector x belonging to the set V, there corresponds a unique vector which we will label as minus x. Okay, this is just a label. This minus has minus x is just a label for the unique vector that we are talking about. And what is this unique vector doing? Such that x, when added to this minus x, or minus x added to x, will always give you the 0 vector. This is basically the existence of a unique additive inverse. Okay, so these properties are for vector addition. Okay, the next set of properties or axioms that we'll see will be for the scalar multiplication. So this is all related to how the scaling up of a vector is. Okay, about the scaling of a vector. Okay? Hence the term scale. So the first property is for all alpha belonging to. So you take any element from the field. Okay, if you remember, we said a vector space over a field. Okay, we said a vector space over a field F. So the elements of a field will be used in this vector space. Okay, the definition of this vector. So they have a role. So the first property is you take up any element from the field, and any element or any vector from the set V, the scalar multiplication, okay, which is denoted by alpha into x. Alpha is from the field, and we term this alpha as the scalar, and x is from the set V, and we term x as the vector. So the scaled version of x, which is scaled by the scalar alpha, will also belong to the set V. Okay, so this is again closure but under scalar multiplication. The first one that we had seen was closure under vector addition. This is closure under the scalar multiplication. Okay, so this is the first property. Second property, alpha beta belonging to the field F and x belonging to the set V, scaling up a scaled vector is same as taking the multiplication of the scaling quantities and then scaling up the vector. You first scale up the vector x by the scalar beta, and then you scale up the vector beta x by the scalar alpha. This is same as scaling the vector x by a scalar which is given by the product of alpha and beta. Okay. For all x in the set V and element 1 in the field, okay, it will always give back the same vector. Okay. Next, the next, so in some cases, okay, I forgot to mention this. X plus y is the vector addition or the sum of the vectors x and y, and alpha x here is known as the scalar multiplication, or is also called as a product of alpha and x. So we have 5 relations that have come out, or 5 axioms that have come out from the vector addition, and 3 from the scalar multiplication. 2 more properties that we need to satisfy. What are the 2 more properties? They are the distributive properties. Now, this essentially is going to establish a relationship between the scalar multiplication and vector addition. Okay, the first one is for all alpha in the field F and a pair of vectors from the set V, alpha product with x plus y is same as alpha x being added to alpha y. This is known as distributive with respect to vectors. With respect to vectors, because the scalar multiplication is being distributed over the vector addition. Similarly, for any pair of scalars from the field F and a vector from the set V, alpha plus beta product x is same as alpha product x plus beta product x. This is distributive with respect to scalars. So basically add two scalars and then the resulting scalar scales up a vector is same as scaling up the same vector by the individual scalars and then adding up the scaled versions. Okay. So for a set to qualify as a vector space over a field F, it has to satisfy certain properties or axioms with respect to the vector addition, the scalar multiplication. So it has to satisfy, if we go back, it has to satisfy the closure property, the commutative property, the associativity, then existence of a unique additive identity and existence of a unique additive inverse as far as the vector addition is concerned or the sum of vectors is concerned. As far as the product of a scalar and a vector is concerned, it should again have the closure property. So the product of a scalar and a vector should be in the same set V. Then alpha multiply scaling up of a scale vector is same as scaling the vector with the net scaling factor alpha into beta. And then the richest element 1 in F, okay, the identity element of F, such that if you take a scalar product of 1 with respect to any vector in the set V, then you will get back the same vector. So this is as far as the scalar multiplication is concerned. If you go to vector swim, then we have two distributive properties. One is distributive with respect to the vectors. So if you scale up addition of vectors, then it is same as adding the scaled up vectors. And the second is if you add two scalars and then scale up a vector, it is same as scaling up the same vector by the individual scaling factors and adding up the scaled vectors. So for a set to for a set of vectors to be classified as a vector space over a field F, all these properties have to be satisfied by the set. Okay, so we'll see some examples. What are those examples? You can, let's start with this. A set of integers is this a vector space? You take any two, so we'll start the very beginning. So here you take any two integers in the vector space, if you add them up, you get back the integer. So the closure property is satisfied. This also satisfies the commutative property, the associativity. There is a unique additive identity, which is 0, and each element has a unique additive inverse, which is basically the negative of the element of the vector itself. Okay. Scalar multiplication. If you take any element from the field Z and multiply it with the element in the set Z over the vector set and the integer Z, what you get back is essentially the same. If you take any element from the field Z and multiply it with the element in the set of integers Z, then what you get back is again an integer which lies in the set Z. Okay. So closure with respect to scalar multiplication is satisfied. You can also verify that, of course, 1 multiplied with the integer will always give you back the same integer. And you take any two elements from the field and multiply them and then multiply this output. So let's say you take the integers 2 and 5, and multiplication is 10. So you take this 10 and multiply to integer taken from the set Z. Let's say you take up the integer 3. 10 into 3 is 30. It's the same as 2 being multiplied to 5 being multiplied to 3. So 5 multiplied with 3 is 15. 2 with 3 multiplied 2 you get 30. So it's the same what you get. Okay, scalar multiplication. So then you can check whether the distributive properties are satisfied or not. Okay. Now a set of rational numbers over the field of rational numbers. This is also a vector space. It is a vector space over the rational numbers q. Similarly, a set of real numbers over the field of real numbers. A set of complex numbers C over the field of complex numbers. Set of complex number C's over the field of real numbers. Set of real numbers R over the field of rational numbers. Set of real numbers R over the field of integers. Rather, I would suggest that verify if these are vector spaces or not. Verify if these are vector spaces or not. Please note that the vector space 4 defined in number 4, example number 4, is different from the vector space defined in example number 5. It's because the field over which the vector space is defined, the field associated with the set is different. In the example 4, the set of vectors of the set C is associated with the field of complex numbers, but in example 5, the set of complex number C is associated with the field which is reals. Okay, so you have to be careful. So these are some examples that you have. A lot more examples, we'll discuss them in the forthcoming lecture. We'll take up some sets and we'll go through those properties and see if we can establish whether they are vector spaces or not. We'll stop here.